We are discussing about context-free languages. In the last class, we have seen that push-down automata can represent context-free languages, and in the acceptance of a string in the language, we learned about two different criteria for acceptance. They are empty stack acceptance and final state acceptance. Given an input string W, in the empty stack acceptance criterion, the input string W is considered to be accepted if and only if the processing of the input string W ends in a state where the stack content is empty. So, in this case, the push down automaton accepting a string regardless of whether the status of the last state is final or not. It just depends on the stack content. If it is empty, the input string is accepted, and if the stack is non-empty, the input string is rejected. Empty means even the bottom of stack symbol is not there. That is the first criterion. The second criterion is final state acceptance, where an input string W is said to be accepted when the processing or reading of the string ends in a final state. So, in the second criterion, it depends on whether the last state is final or not after you finish reading the input. And in this criterion, the content of the stack when you finish reading your input is not considered for deciding whether it is accepted or not. So, it can be empty or non-empty. And the topic for today is equivalence of acceptance criteria. We are going to prove today that they are equivalent. In what sense? That we can see. In what sense they are equivalent will be stated using two claims. Claim 1, given a push down automaton A with a final state acceptance, that is the criteria, we can automatically construct a push down automaton A prime with the empty stack acceptance criterion such that their languages are same. So, given a push down automaton which accepts by final state, we can automatically obtain an equivalent push down automaton which accepts by emptying the stack. And the second claim is the opposite direction. If you are given with a push down automaton which accepts by emptying the stack, then you can automatically construct an equivalent automaton A prime which is accepting by entering a final state. So, this is the objective for today. We have to prove it. The proof is not difficult, and in fact given a push down automaton any of this kind, we can automatically construct a push down automaton which will accept by both the criteria, that is, which will accept by entering a final state as well as emptying the stack. That is what we are going to do. We will discuss two constructions. One, taking a final state accepting automaton and converting it into an equivalent one which can accept by both the criteria. The other construction will take a push down automaton which is accepting by emptying its stack, and we will construct an equivalent one accepting by both the conditions in criteria 1 and 2. Let us now consider the first construction. We are taking as input a push down automaton with a final state acceptance, and we can try to create an equivalent automaton which is going to accept by both the criteria empty stack and final state. Suppose you are given with the initial configuration of an automaton. So, initial configuration, a configuration can be defined, and given this, it means the machine is in the start state, read head is pointing to the first input simple, and only the bottom of stack is there as the content of the stack. And suppose in this automaton, and this notation we have to see a triplet where the first is a state, the current state. What is the current state of the automaton? Which is yes. And the next is what is the unprocessed part of the input to be read, because we haven't read any simple, it is the entire input. And the last one is the content of the stack. And not that here the content is just bottom, and that is what this is bottom. So, triplet is defining a configuration which is uniquely defined by the current state, the unread part of the input, and the content of the stack. And any push down automaton will start with this configuration for a given input W. That is the start state, entire input W needs to be processed, and only the bot simple is on the stack. And suppose eventually it gets into this configuration, what is it? State is final, the remaining string to be read is epsilon, that means the input W is completely read, and there is a content on the stack. Then by the final state acceptance, you know that after finishing the input you are in a final state. So, regardless of the stack content, you are accepting. That means W is in the language of the automaton. Pictorially, this is that configuration. You are in state F, input is completely processed, so the remaining input is epsilon, and this is the content of the stack. So, this is what you have as an automaton. Now, the question is, we want to empty the stack because we want to accept both by final state and empty stack. Now, the question is, once you get into this configuration, can you empty the stack? Not that the final configuration is the state F, input to be processed is start string, and there is a non-empty content which you call it as gamma. Gamma is actually this string x1, x2, etc., xn followed by bot. Now, can we manage it by just adding these transition? What is it? From that state, without processing an input, you pop out all the simples is what I am telling. X is any simple in gamma including bot. So, whatever be that simple, remain in the final state, just pop off. That is what you do. So, definitely in this case it will empty the stack. So, in this particular case you are accepting then by both the criteria, by final state as well as stack empty conditions. So, what we do is, once after you finish the input, you are in a final state. In that final state, remain in that final state, no need to consume any input, just take out the top of stack simple for all the simples. So, you can apply this transition as long as simples are there on the stack. So, eventually you will empty the stack. question is, can we do it just by this? The answer is no, because you just look at another input. Suppose you start with the start state, entire input needs to be processed, only bot is there on the stack, and eventually you are getting into this situation. What is it? You are in a state P, which is not a final state. You emptied the input string, that means nothing is there on the input to be processed. And what is the stack content? Stack content is again empty. See, this configuration is saying state is P. Maybe we can draw that. You started with this configuration W as this, you reached into this. So, the state is P, which is not a final state. The input to be processed is empty, nothing is there, and stack is empty. And see, this is an automaton accepting by final state, and this is not a final state. So, no doubt the string W is rejected. Now, see, in the new automaton, you will not be able to apply the newly added transitions because you are not reaching into a final state. But see that this string will be considered as accepted when you apply the empty stack acceptance criterion. So, we wanted to construct an automaton which accepts by both the empty stack acceptance criterion and final state acceptance criterion. I hope you are getting me. It will fail if you just add these transitions alone. You will fail because there could be some inputs for which the original automaton A rejects that input by emptying the stack. That is always allowed. If you finish in a non-final state, regardless of what the stack content is, if the state is not final, you reject. In that case, if you just say that it is also accepting by empty stack acceptance criterion, you will fail because the string which is rejected by A will be accepted by A prime when you apply only the empty stack acceptance criterion. I hope you are getting me. For the interest of time, let us proceed. And we so that this is an unsound construction because it is accepting a string which is not in the language. Now, what to be done? What to be done is, what you can do is, you just come up with a new state and call it as the start state of the automaton A prime. And the only change is, you are now having a new bottom simple, double bot, and what you do then is, you add this transition. So, what will happen? You are saying, if you are in the state S prime, then without reading an input, without reading the first simple, and if you have already the newly added bot, double bot in the top of stack, what you do, you change the state to the start state of this automaton A. So, after that A will work, A will execute the input, and and what you do in the stack, above this double bot, you insert or push the original bot simple for the given machine. So, this is what I am trying to tell. So, now you see that when A wants to execute, it is starting in this configuration. Without its knowledge, a new bot simple which only A prime can see is put on to the stack. Now, everything is done. Now, what you can do is, now you have reached into the starting configuration of the original machine, and the original machine cannot see anything below its bot. Now, suppose there is a string W which is accepted by the original machine, then definitely you will come into this situation because the original machine accepts means it is entering into a final state. So, now what will happen? We can add this transition from the final state without processing an input. Whatever be the top of stack symbol, you pop it out and go to a newly added state called T. In that state T, you are going to empty the stack even including the double bot. So you need that transitions, that is from T without consuming an input, you take out all the stack impulse, so you will eventually empty it. So definitely in this case you will empty it by applying these transitions, and not that by applying this transition you will get into T. Previously the original machine stopped in this configuration where the machine A accepted. It is immaterial what the stack content is. What the new machine will do, it is saying if you are in state F without reading any input, whatever be the top of stack symbol, you change your state to T and pop out this symbol. So this is what is happening. Then what is T saying? While you are in T without reading input, whatever be the top of stack symbol, you just pop it out. So eventually T will empty the stack content including the newly added bottom. That is including, X can be even that simple. So definitely you will empty it. So now you see that if you make T as the only final state of the newly constructed PDA, then T is a final state, so accepted by final state as well as accepted by empty stack. Now maybe you look at a string which is not in the language. So what the original machine will do? The original machine will stop in a state P, input is completely processed and nothing is there on the stack. This was the problematic case before. Now see, W is not in the language, and this is the configuration where the original machine A stops, and note that now the stack is really not empty, it is having the newly added bottom, and because we have not added any transitions for non-final state, nothing will happen. So for a string not in the language, the stack cannot be empty and the state is not final, so it cannot accept by any of these criteria and we are done. Maybe now we can make it very formal. So given or push down automata with the states, input alphabets, stack alphabets, start state, transition function, bottom of stack symbol for A, and set of final state. You can define a new push down automata. In that you just added two states, S prime and T, right? You know why S prime, to put that double bot. Then input alphabet is not changed. To the stack alphabet you just added this double bot in the new machine, and not that the newly added state S prime is going to become the start state of A prime. The only purpose is putting this double bot below the bot of the A machine. And delta prime, the newly the transition function for the new automaton that we will see later. And the bottom of stack symbol for the new machine A prime is going to be the newly added bottom. And the set of final state is singleton, and that is a newly added final state. And recall that from any final state of the original machine, there is a transition without consuming the input. Whatever with the top of stack symbol, you are moving into T. I hope you remember it. And what is the newly defined transition function? All the transition relations or function maplets in the original machine, delta is there as such. In addition to that, you are adding certain transitions. Just recall what all things we added. The first transition to put this double bot onto the stack and moving to the start state of the original machine, we have one transition. Then once you get into a final state without processing an input, regardless of what the top of stack symbol is, you are moving into T, the newly added final state, and taking out the top of stack symbol. And once you get into T, you are emptying the stack by using these transitions. I hope you remember, just formally writing it. No need to worry about it. Maybe you can verify it offline. Now you can argue that if W is a string in the language, then W is also a string in the newly language of the newly created automaton and vice versa. So you can prove that the construction is correct if you want. Now the other construction, for the interest of time, let me proceed. Now you are given with an empty stack accepting automaton, and you want to construct a new one accepting by both the criteria. And now suppose you start with this configuration, the start state, the input string as such is there to be processed, and only bottom of simple in the stack, the initial configuration for any push down automaton. And suppose eventually it happens like this, that is, after processing the complete input, nothing more to be processed, the stack is empty, then regardless of the state you will be accepting. W is in the language. So this is the corresponding configuration. So you finished reading input, you are in some state, you don't mind whether it is final or not, and the stack is emptied, and by the empty stack acceptance criterion, then W is in the language. Now to get A prime, we want to enter into a final state, that is an issue. Both the criterion, once you get into this, you want to enter into a final state. That means from P, without consuming any input, you have to move into a newly added final state, you can say. But unfortunately, to add a move, you need a stack simple, and that is the problem here, and that can be managed. We need to have a stack simple, and that can be managed with the same trick. What you do is exactly what we did previously, and here you wanted to have a stack simple. Here for that you can utilize it. Now see, this will be the configuration where the original machine starts its processing here, and then if you run the original machine A on this, you will eventually get into this, because you empty the stack when you completely process the input you accepted. So this is the configuration of the newly defined push down automaton. For the original automaton it is emptied, but for the new automaton one more simple is there. Now you can add this transition. For all the state P, without processing an input simple, if double bot is the top of stack, that means the original machine already have finished its stack, then what you do, you jump into the newly added final state and you pop out, and you can easily verify that this is correct, and you can formally define it very similar to the previous construction. The structure is very same, and this is again same. The only thing is that here final states are not relevant for the empty stack accepting automaton, and so what you are doing is for all P, to manage the last situation, you will make a change to the newly added final state, that is here, by just popping out the newly added bottom symbol. And you can here again argue that if a string W is accepted by the original automaton A, then W is accepted by the newly created automaton by both the criteria. Similarly, if W is accepted by the new automaton by any of these criteria, then you can prove that W is accepted by the original automaton. If you want, you can have a proof by applying the principle of mathematical induction on the length of processing or the length of the string. And with this we are coming to the last part of the lecture, where I am giving you two exercise problems for you to practice and understand how these constructions work. Here you are given with a empty stack accepting push down automaton. You are asked to apply the second construction to come up with a new automaton and accepting by both the criteria. this is the other direction. You are starting with a final state accepting automaton and going to get an automaton which is accepting by both the criteria. Okay. Today we proved that the empty stack and final state acceptance criteria are equivalent. So regardless of what criterion is used by a PDA programmer, push down automata programmer, we can automatically translate it into an automaton or a program for a non-deterministic push down automaton, which will work by both the criteria. Thank you.